Hi guys, in this video we'll be discussing about the error calculation in ammeters. Uh, so previously we had seen how we can do the error calculation in Wheatstone's bridge in one of the previous videos or from one of the previous lectures. So here what we are going to do is that we are going to apply the same logic in case of ammeters, any of the ammeters, like let it be a PMMC instrument or a moving iron instrument or a electrodynamometer type instrument. Any of these instruments, all these instruments generally measure current, but they can also be used as voltmeters as well, with the change in the design. But if they are used as ammeters, but generally they sense current, whereas the electrostatic meter senses the voltage. But all the other meters like the PMMC or the MI, moving iron, or the electrodynamometer type instrument actually measures current, but it can also be used for measuring voltages. Now the general characteristic of an ammeter is that for ammeter we generally connected the meter in series with the circuit element through which the current has to be measured, series with the circuit element uh, through which the current has to be measured. So current to be measured. So the problem here is that the ammeter will have a small internal resistance, right? Internal resistance is going to be internal resistance will affect the measurement itself. It definitely has a internal resistance, and that is going to affect the measurement. So that is the major problem over here. So depending upon the internal resistance, we'll have certain errors in the measurement, and we are going to address those errors, and we'll be looking at how much this quantity would be and what are the how this can be minimized in any circuit. That is our major aim. Now the answer to this question is very simple. The internal resistance should be very less in comparison to the circuit elements. Definitely that is a factor. So ideal internal resistance of an ammeter should be close to 0 amperes. That is the ideal internal resistance of an ammeter. But in practical case, this is not actually possible. Practically, the coil is definitely going to have a particular resistance which is going to contribute to the internal resistance of the ammeter. So if we take a simple circuit and if we look at what is the error, I mean, we can understand this by looking at a very simple circuit. Let's say we take a simple voltage source. Let's say it's of 10 volts, and then let's say we take a resistance of, let's say, 8 ohms, and let's say you have a ammeter over here, and let's say this ammeter has a resistance of 2 ohms. The internal resistance of the ammeter is 2 ohms. Now if this is the case, what should be the true value of the current that has to be measured? The true value is how much? The true value is 10 volts divided by 8 ohms without the ammeter, isn't it? Now the moment you introduce an ammeter into the circuit, which is having an internal resistance of 2 ohms, what happens? The measured value value turn out to be 10 divided by 8 plus 2, which is 10 by 10. That is this value comes out to be 1.25 amperes, but this value comes out as 1 ampere, isn't it? So there is definitely a difference in the measured value and the true value. So now what we are going to do is that we are going to find what is the error in this case. Now the error, and the absolute error in this case, would come out as absolute error would come out as 1.25 minus 1 ampere, that is 0.25 amperes, and the relative error would come out as 0.25 divided by the difference in the measurement divided by the true value. Now the true value is 1.25, so the relative error is the true value minus the measured value by true value, which is 0.25 by 1.25. that would be 1 by 5, which would come out as 20%. The 20% would be the 20% would be the error in this circuit. So now, which is a very high value in this case, because you don't want a measurement to have an error percentage of 20%. So this was a simple example that we took over here, because of which you might end up getting a percentage error of 20%. But this in practical scenarios, we design the ammeter in such a way that the error is very low in the sense much lesser than 20%. So now the easiest method to find the error, or whenever we design a circuit and when we want to place a ammeter into a circuit, and we design the ammeter in terms of that circuit, and the easiest way to do is by using the Norton's equivalent. I hope you must have already learned what is Norton's equivalent or Norton's circuit. Norton's equivalent circuit. By finding the Norton's equivalent circuit, you can easily find what should be the value of the resistance of the internal resistance of the ammeter in order to minimize the error. Or so in Norton's equivalent circuit, any states that any circuit can be represented as a current source in parallel with a resistance, and to which you can connect a load, right? This is the current source IN, this is the parallel resistance, and here we can connect a ammeter, and we can find what would be the current that is flowing through this ammeter. At right now this might seem a bit confusing, but let's take a circuit and do this. Let's evaluate the Norton's equivalent. Right now, once we look at a circuit, this is going to be very much easy, and you would find this as very simple, how to calculate the Norton's equivalent, or how to calculate what should be the resistance, or what would be the error depending upon the resistances. So let's look at a simple circuit, which might look a bit complicated, but actually it's a very simple circuit. So let's take a circuit. So we have a voltage source 1 volt, Then we have a resistance, and then we have another voltage of 5 volts, and then we have another 10 ohms. Let's say this is 5 ohms. Let's say this is another 10 ohms, and let's say we have a 1 ampere source, and let's go with another 5 ohm resistance and another voltage source of 2 volts. Right now, let's take a random branch onto which you want to put an ammeter, and let's say you want to put a ammeter in this branch. Right, let's put an ammeter in this branch, and let's find what would be the error with respect to the resistances of this particular ammeter over here. First, let's find what would be the resistance, what would be the current that would be flowing through each of these branches from the circuit. That's going to be a very simple analysis, and let's analyze the circuit. The circuit looks very complicated, might look complicated to a few of the students, but this is not that complicated. This is a bit, and this is a simple circuit. So let's do the analysis for the circuit. So let's say this is our ground, right? And let's say this is the potential. Let's take this as 0 volt. Let's take this, and the potential over here as 0 volts. So the potential at this point would be, you have a 5 volt source over here, which makes this as potential over here as 5 volts, right? At this point. Now at this point the potential would be, this is 0 because it's connected to here, this would be 1 volt. Now let's take the potential over here, this is 0, this is 2 volt, so the entire node is 2 volt, right? Now what would be the current over here? The current in this branch would be 5 minus 1 divided by 5, which is 5 minus 1 divided by 5, that is 4 by 5 amperes. So this current would be 4 by 5 amperes. Now we have 2 volts over here, so this is 0 volt, this is also going to be 0, and this is going to be 2 volts over here. So the current would be 2 by 5, 2 minus 0 by 5, that is 2 by 5 amperes, right? There's a 1 ampere that is coming out over here, and this potential is 2 volts. The potential at this point is 2 volts. Now we can find what would be the current that is flowing between these 2 points. So here we have 5 volts, here we have 2 volts, so the current direction would definitely be in this direction. That would be 3 volts divided by 10 ohms, right? So the the potential difference between these 2 points is 3 volts, and the resistance in this case is 10 ohms, so you'll have 3 by 10 amperes in this case, also 3 by 10 amperes in this case, and so you have 3 by 10 plus 3 by 10 coming towards this direction, so that makes it 6 by 10 amperes in this branch. Let's find out what is the current in all the branches. So 6 by 10 is coming towards this branch, 1 ampere is coming from here, from this 1 ampere source. Now 6 by 10, what would be the current over here? That would be 6 by 10 plus 1 is going to be 16 by 10, or you can write it as 8 by 5, 8 by 5 amperes. So 8 by 5 amperes is flowing towards here, out of which 2 by 5 flows downwards. So what is left over? The leftover is 6 by 5 amperes is flowing to this direction, right? I think by now we have got all the currents in almost all the branches, so that's more than enough for the time being. So we wanted to measure what was the current through this branch. Now we have already found what is the true value of the current that is passing through this branch, which is the true value of the current is 3 by 10 amperes, right? Now this is also same as when we take the Norton equivalent. This is also same as the IN of the Norton equivalent. The current source, the value of the current source for that Norton equivalent is 3 by 10 amperes. Now if we want to find what is the resistance, we have to find the resistance by looking from this point over here. We need to look the resistance from this point by opening these 2 points across the ammeter. So if you open the 2 points across the ammeter, for finding the current, we short this path between the ammeter and we find what is the current by removing the ammeter. But right now we are going to open the circuit and we are going to find what is the resistance, right, by looking from this point. Now there is a 10 ohm resistance over here, there is another 10 ohm resistance that is there over here. Now what we do is that we'll open the current sources and we'll short circuit the voltage sources in this case. So we have a current source, we have already opened it, so there is no branch over in this current source. Instead we are going to put only the resistances right now. So we have a 5 ohm resistance over here and we have a voltage source which is going to be shorted over here, and then we have another voltage source over here which should be shorted over here, right? And then we have another current source, another resistance with a voltage source again connected over here. Now if you look at this, when we look from this direction, this resistance, there is a short circuit in parallel to this resistance, right? So in parallel to this resistance we have a short circuit over here, which means that this resistance is not going to be valid in this case. Similarly, there is a parallel short circuit with respect to this resistor. Again, we don't have to take this as a resistor as well. Again, if you look at this resistor, there is again a short circuit path which is parallel to this resistance. So this resistance value will also become 0 because there is no current which would be passing through these resistances, because there are parallel paths which is having no resistance. So in this scenario, the only resistance that would come into the picture would be the 10 ohm resistance, right? So the value of Rn would be equal to 10 ohms and the value of current IN would be equal to 3 by 10 amperes, right? Now we can draw the equivalent circuit. The equivalent circuit would turn out as the current, a current source of 3 by 10 amperes and a parallel resistance which is of a resistance of 10 ohms, and then in parallel to this 10 ohm resistance you can connect our ammeter, right? So from this circuit we'll be able to find what would be the current through the ammeter, right? Now let's say we'll take a few cases in this for this ammeter. Let's say the resistance the internal resistance of ammeter. Let's say we'll take 3 cases. Let's say we can take 10 ohms, 5 ohms. Let's take 4 cases, 1 ohm, and one more case, which is 4, that is 0.1 ohm, right? And we'll see what is the error in all these 4 cases, right? Now if this is case 1, in case 1 the internal resistance, we are taking it as RA of the ammeter as 10 ohms. Now if the resistance of internal the ammeter is 10 ohms, what would be the current that would be passing through the ammeter? Current passing through the ammeter would be equal to the total current. The total current is IN into, we'll apply the current division rule, which is opposite branch resistance divided by the total resistance, which is Rn plus Ra. So here we would get it as 3 by 10 into Rn resistance is 10 ohms divided by 10 plus Ra is 10 ohms, right? Now the measured, we are basically going to find the measured value of current by the ammeter over here. So you'll get it as 10 and 10 gets cancelled, you'll get it as 3 by 20 amperes, right? And this would be the measured value of the current. So the absolute error, we already know the true value. The true value is equal to 3 by 10 amperes. Now the absolute error would be equal to 3 by 10 minus 3 by 20, which would be 6 minus 3 by 20. We'll take the LCM, so 6 minus 3 by 20 or 3 by 20 amperes would be the, so since it's an error, we're not going to put any unit, but we are finding the error in the current, so it's up to you. You can put it as 3 by 20 amperes is the error. So if we look at what is the relative error in this case, the relative error would turn out as the difference, that is 3 by 20 divided by the true value, which is 3 by 10. When you divide these two values, you get it as 1 by 2 percentage, which is 50%. 1 by 2 into 100, right? Relative error into 100 percentage. So this would turn out as 50% error, which is a very huge value in terms of measurements, right? So definitely you can't have a value that is in this range, right? Now let's look at the second case. For case 2, we are taking the resistance of the ammeter as 5 ohms, right? So if we take the resistance as 5 ohms, the measured value of current would be equal to the total current 3 by 10 into 10 divided by the resistance of the parallel resistance. So this is the total current into opposite branch resistance. So this was the circuit, right? You had an ammeter parallel resistance of 10, and then we had an ammeter, current source IN, RN, and then an ammeter. Fitting the internal resistance of ammeter is 5 ohms in this case. We'll get as 3 by 10 into 10 divided by 10 plus 5, that is equal to 3 by 15 amperes, right? Now this is the measured value of the current, and let's say let's find what would be the absolute error. The absolute error would turn out as 3 by 10 minus 3 by 15. We can take out 3 by 5 in this case from both these values, so which would turn out as 3 by 5. If we take it out from both these fractions, we'll get it as 1 by 2 minus 1 by 3. That would be 3 minus 2 by 6, that's 1 by 6. So we'll get it as 3 by 5 into 1 by 6. Cancel out this 3's, we get it as 2. Finally we'll get it as 1 by 10, which is the absolute error. Now if you look at what is the relative error in this case, the relative error would be equal to the difference which is the absolute error divided by the true value, 1 by 10 divided by the true value is 3 by 10 into 100 percentage relative error. So 10 and 10 gets cancelled, we get it as 1 by 3 into 100, that is 33%, 33.33% would be the relative error, 1 by 3, right? Now let's look at the case 4. Case 3, we will get it as RA is equal to, I think we're taking as 1 ohm. If it is 1 ohm, then the measured value of current would be equal to the total current, 3 by 10 into the opposite branch resistance is 10 divided by 10 plus 1, that is 11, right? Or you can do this 10 plus 1, the total resistance written as 3 by 11. The absolute error would be 3 by 10 minus 3 by 11. If we cross multiply this value, we'll get it as 33 minus 30 by 110, that is 3 by 110 is the absolute error, and the percentage relative error would turn out as percentage relative error would be 3 divided by 110 divided by 3 by 10. We can get it as this 3 and this 3 would get cancelled, 10 and 10 would get cancelled, we get it as 1 by 11, which is the percentage relative error, 1 by 11 into 100 percentage, which would turn out as 9 point something error, or very close to 10 percentage, 9 point some values would get, which would be very close to 10% error. Now in case 4, if we take the ammeter resistance as 0.1 ohms, the measured value of current would be equal to 3 by 10 into opposite branch resistance divided by the total resistance. So it should be 10 plus 0.1, that would be 10.1, and you would get the answer as 3 divided by 10.1. so this would be the measured value, which is very close to our the absolute value. So let's look at how much this would come out as. So 3 divided by 10.1, we'll get this value as 2.297. Yes, 0.297, 0.297 amperes, but the true value was 3 by 10. The true value was 3 by 10, which is 0.3 amperes. Very close. This is very close. We can also calculate what was the value of 1 by 11. So let's calculate 1 by 11. 1 divided by 11 come out as 9.09. Yeah, so let's put that value over in the previous case, 9.09%. So which is closely equal to 10%. That's it. Now let's find what would be the percentage of relative error. The percentage relative, we'll find out what is the absolute error. Absolute error is going to be 0.3 minus 0.297, that is going to be 0.003 amperes, or 0.003 is the absolute error. And if we find what is the relative error, the percentage relative error in this case is going to be 0.003 divided by 0.3 into 100 percentage, which would come out as 3 divided by, I'm going to put 3 points to the right, so we'll have to put 3 points to the right over here as well. 300 into 100, so get it as 100 over here. 100 is 1% roughly. So this value will come out as 1%, which is quite low in this case, but if you can make it even lower, that would be even better. So basically the general formula over here, we can write it as we know the true value in this case was 3 by 10, which is the IN, or you can also say that is the short circuit current itself, right? Now the measured value in this case is 3 by 10 into, or let's write the general form. The measured value is going to be in this case IN into opposite branch resistance, which is Rn, divided by the total resistance Rn plus Ra, which is the general form. So we want this approximately equal to IN itself, because that is the true value we have already seen from the circuit. So if we want this very much approximately equal to IN, we need to have this value Rn plus Ra approximately equal to Rn. Only then, approximately equal to Rn, only then we'll have IN, the measured value, to be equal to the true value. For getting this value, Rn plus Ra approximately equal to Rn, we'll have to minimize the value of Ra. So we need to minimize the value of Ra such as Ra is very much lesser than the Norton equivalent for any circuit, Norton equivalent resistance. So this is the condition that is required in order to get the minimum possible error for an ammeter. So this is our final conclusion from this circuit and from this analysis. So I hope you understood this video and this lecture. Thank you guys, and have a nice day.